Okay, we continue. Now we are in the last week.
As with any other digital technology, both the scope and the capabilities of applications using IoT is also expanding fast. If you look at the future trend of what's in the cards, how companies are now beginning to emerge out of simple siloed IoT applications to improve a particular process or so, now they're thinking about building the full visibility of supply chain end to end, from upstream suppliers to downstream, logistical partners and customers, so that they're not just looking at information about a particular product, but the entire process and as much information that could be made visible as possible. So that's one trend that we see, and we're also seeing more customized sensors for unique applications. And we have sensors that come in with kind of powerful chips so that they have intelligence in them. For example, what we're also saying is that more and more dedicated sensors will actually look at connecting not just the manufacturing process, but also focusing on the talent and then operations of workers working in factories. For example, there are sensors that are kind of maybe sometimes put in body of the workers to see what kind of movements they're doing, and then collect information from those sensors in order to improve the design of the product itself to make it more ergonomic, and then improve the strain on the physical strain on the body of the employees working on the product. And those are some dedicated sensors. Now, talking about dedicated customized sensors, we're also now seeing sensors which are now more intelligent and are learning. Right, there is embedded intelligence. Thinking about referring to the edge computing we talked about, there are powerful chips within the sensors that actually so that the sensor can learn over time. And we'll talk more about when we refer to or when we come to the section on artificial intelligence applications in manufacturing. We also have more exciting applications in other industries as well. Now we're talking in terms of breath sensors, where the sensor can actually kind of sense our breath and then probably decode in terms of what kind of disease we have and how serious or critical is it, is the problem that we have, and things like that. They're now talking about microsensors, like where there are possibilities that these are all in the works in the R&D, where the possibilities of putting microsensors in blood vessels to kind of measure the blood pressure. Right now, right now we pressure, we measure the pressure from outside. Can we do it from inside? That's the real time data, right? As things happen. So these are some of the examples of where this sensor technology is moving. This broad spectrum of some of the future trends and a lot more. Because remember, this is fueled by the advances in communication technologies, advances in miniaturization and microsensors and electronic circuits in terms of how powerful they can get. All these capabilities are coming together to kind of define what will be the future trend. And also, as I see from being siloed applications, IoT sensors and what we call as the integrated manufacturing, the Industry 4.0, all these technologies, concepts coming together and connected through sensors, in a way that actually enhances the potential for the application. I think that's also one of the future trend, how IoT will evolve as one of the threads that actually connects this platform of the future of manufacturing.
Okay.
So Anil, can you guys actually give us an idea, because with your rich experience in this industry, you've seen in the past, you've seen presented what kind of applications companies are putting in place where we are. In the future, next 3 to 5 years, what do you see? What is the trend you see in this IoT applications being used for manufacturing companies?
So one thing which we are seeing is the adoption is more in terms of making the operations more predictive, in the sense using the data that is being collected, getting the insights from the data, right? So going forward, the operations will be more data driven for sure, and not just data driven, right? Now with the kind of technologies and capabilities that this technology provide, it would move into the zone of applications prescribing a lot of actions to the operators, right? So it would be more in the prescriptive zone, where the system is sensing certain deviations, and in order to avoid either event, it is prescribing what can be done, right? So that's where we call the human in the loop, where it could be in a recommending mode, where it is recommending a certain things to be done by the operator, or it can go to the extent of actually applying that on the control layer in the shop floor to the actual machines, right? The second aspect that we are looking at is also the ability to consider or digitize the knowledge that are there with the operator. Till so far, we have spoken about data coming in from the machines, data coming in from the different sensors, right? But the other aspect that we are looking at is also how we can use the tribal knowledge, the experience of the operator, also to contribute to this construct, the autonomous and self-optimizing construct. So that's something which we are focusing on, wherein we bring in the data aspect of it, and we bring in the knowledge that exists with the operator of having, they come with a lot of experience. So how that experience also can part of this solution construct.
That's very interesting. So basically, what you're saying is that the human in the loop concept is very interesting. So these predictive algorithms, with the data, kind of informed, they are now empowering the human, and then we take better decisions. At the same time, there's a two-way street here, because you're also capturing human knowledge to build that, that analytics as well, because they may have decades of knowledge working on that particular space. So you're both able to express it, also you're able to empower and inform them. Okay, great. Thank you so much, both Anil and Sachin. It was a pleasure conversing with you. Thank you very much. Joining us from other part of the world, Pune, India, to share your insights. Thank you very much.
Thank you, Professor. Thank you.
Today, we have Professor Yogesh Gyanchandani from our own University of Michigan. Professor Gyanchandani is a professor at the Electrical Engineering and Computer Science Department at the University of Michigan. He's also the director of our Center for Wireless Integrated Microsensing and Systems. So he's been leading that center for many years now. Yogesh, thank you very much for taking time from your busy schedule. I really appreciate joining us in this course.
It's my pleasure.
Yogesh, you've been at this technology, you've been working in the sensor technology for multiple decades, and you certainly are one of the leading experts in this field. First, can you tell us about the center that you're leading at the University of Michigan?
Sure. So the center, as you said, is for wireless integrated microsensing and systems. Our charter is to pursue research, development, and application of sensor-enabled microsystems through basic research, through education, and also through interactions with industry. It was created in the year 2000 with support from the National Science Foundation, but we have been operating independently since 2010. And we bring together specialists in a lot of different areas that are relevant to creating the system. And we have a collaborative, multidisciplinary environment with a lot of industrial interaction.
Great, thank you. So, Yogesh, this rich experience for the last 2 decades or more working with industry and working on the R&D and the research and development of this technology. Can you tell us some of the trends that you've seen in the last 2 years in the sensor technology, and especially how it's now being used in the industrial context?
Sure. First, I want to remind everybody that even though fundamental research that's done in universities frequently ends up in industry, the path is not always straightforward, and it's not preordained. Funding of academic research is driven by federal priorities established by the peer community through the review process, such as at the National Science Foundation or National Institutes of Health. Solicitations are sometimes driven by professional organizations such as the National Academy of Engineering that sets out grand challenges, and then we try to address some of these grand challenges through solicitations that come out for supporting research. There is also some amount of research that is sponsored by industrial consortia, and typically they will target 2 or 3 nodes, technology nodes out. The federal agencies will try to address more fundamental problems or problems that may be a decade or even 2 decades out. As far as MEMS research and microsystems research is concerned, from an academic point of view, the number of applications is really vast. What we do is we connect the physical, chemical, and biological world to the digital world.
So, Yogesh, maybe can you explain for our learners, what do you mean by MEMS? What exactly is MEMS?
I should explain that. MEMS is micro electromechanical systems, and it's a terminology that's used for chip scale sensors and actuators. So that would incorporate things like acceleration sensors that are used to deploy airbags, or rate of turn sensors that are used for skid control in automobiles. Your cell phone has probably 3 dozen different kinds of MEMS sensors in it.
Okay. So can you give us an example of how MEMS used in one application of my cell phone, for example?
So in your cell phone, and I'm using the term MEMS more broadly. There might be microsensors that are not necessarily electromechanical. They could be using a different transduction method, but just the microphone into which we're speaking right now. It's a sensor, right? And the facial recognition that allows you to access your phone, well, that's actually involves multiple sensors and or multiple microtransducers, as we would say, and just the inertial sensors that tell the cell phone which orientation you're holding it. Those are just, and of course the camera itself is another sensor. Those are some of the microsensors, right? There's a lot of other things, right? So, and we can get into that later. But basically, these technologies, in a fundamental sense, can apply in a lot of different contexts: weather forecasting, environmental monitoring, wearable and implantable technologies, for biomedical devices, health and fitness devices. Then there's homeland security and defense applications, things like chemical sensors, communication systems, micro antennas and the like. Transportation systems obviously use them. Smart homes would use them. There's potentially a lot of applications in aircraft and space probes, and of course in manufacturing and adaptive manufacturing. Any place where you would need to digitize a physical, chemical, or biological signal. Right? The analog world around us does not behave digitally. You have to be able to convert that, those parameters into digital form, and also go the other way to effectuate a change.
Right. Can you give us a manufacturing example, maybe specifically, especially the usage of MEMS in manufacturing?
A lot of manufacturing uses robotics, and robots would use sensors to interface with the environment.
Right.
So, temperature, pressure, these are flow rate, even certain chemical parameters. There may be a lot of other parameters that will be useful depending on the context. Semiconductor manufacturing, in particular, uses closed loop control for a lot of processes, and there sensing is essential. When I say closed loop control, I mean servo control, where you set a manufacturing parameter and you maintain that by sensing, the various conditions and the mass flow rates and so on of the reactant species and adapt to those.
Mm-hmm. Right. Thank you.
So going back to the older point that, okay, well, there's a lot of different areas where MEMS and microsensors can be applied, but not all of them translate to immediate industrial priorities.
Right.
Okay, so which are those that do? So let me pull up some notes here. Give me a second. Mm-hmm. So currently, let's say going out about 2025, the top sectors for industrial use would be consumer, automotive, industrial, medical, defense and aerospace, and telecom. The consumer sector is the largest. It's projected numbers for 2025 are around $11 billion, I think driven a lot by the cell phone market, with a CAGR of around 8%. So $11 billion on the consumer side. But it's not the fastest growing. Probably the fastest growing is telecom. But that's a small base right now. It's only a few $100 million at the moment, and maybe it'll get up to $250 million. But it's growing quickly. Automotive has always been one of the mainstays, and that's maybe a couple $1 billion, but with a slow growth rate, around 3%.
That's very, very useful. Thanks, Yogesh. Also, I want to actually ask you, your deep expertise in the technology. Can you give us an idea in the next 3 to 5 years, the future trends in this technology? I remember a conversation that you and I had a couple of years back, like when I remember you explained to me that the emergence of the ideas of sensors being put in liquids and in oil, for example, you can track them movement. You talked about a couple of those. So, for our learners, can you tell us some of the new trends that are coming, what we can expect in the next 3 to 5 years?
The industrial sector, it has maybe a growth rate of around 9% and maybe about a $2 billion market. we have been working for
We have
a
been working
number of
for
years on
number of
sensors for harsh
years
environments.
sensor
These have potential use
applications,
in space applications. So that's very exciting and
very
very fundamental in a sense, but it doesn't drive a large market.
Well,
There are similar harsh environments encountered in manufacturing and in mining and oil and gas extraction, where these sensors can be used to diminish the environmental impact. To do things, do exploration and production more smartly. So we've been working on some of these sensors. There are some major challenges in going into harsh environments, and we've been trying to address those. I think maybe that's one of the things you may recall from our earlier conversations. And another aspect of that is also monitoring water and air quality. So there's a lot of interest in doing that, and we have a big program in that in air quality monitoring, and we have previously done some work in water quality monitoring. But air quality is, in a sense, even more important because you can control what you drink, but you can't always control what you breathe. And the importance of this has been, of course, even further underscored by this recent pandemic and the easy transmissibility of viruses. But even if you just look at the non-biological pollutants, particulate matter, you've heard of PM 2.5, PM 10. Particulate matter has a tremendous impact on health, and all the developing countries with growing economies have significant problems and reduced life expectancy and a tremendous amount of lung disease associated with this. And then there's also the invisible volatile organic compounds that you have to worry about. In the West and in a lot of the more developed countries, the attention has turned to this, although it hasn't quite hit the headlines yet in some of the developing nations. But there are carcinogenic chemicals such as benzene that are associated with gasoline production and refinement and usage that can be and should be monitored. And we've been working on technologies for those, and some of those have been spun out into startup companies.
Great, thank you, Yogesh. So those are fascinating applications, and so if I ask you to kind of see tell us where are the business impact the most, right? In terms of the size of the market and also potential business applications for companies, and also it looks like, would I be right if I say that monitoring air quality may be a very attractive market opportunity?
Yes, I believe so. I do. I believe that it could be very attractive. It's I don't. The numbers are not that big yet because the technologies have not matured, but it's coming. This could be democratized. You can envision a VOC monitor in as many places as you would have a carbon monoxide monitor, which is in every home, right? It could be embedded in a thermostat. And you can go a step beyond. If you look at, say, a subsequent technology node where these can be personal safety monitors. So it would be on your cell phone, or you'll be able to wear one. Somebody with compromised health, maybe with asthma or high sensitivity to chemicals, could simply carry one around if the price and performance were appropriate.
That's great. That's fascinating. I mean, I can imagine. So that becomes a personalized application for everybody. They can decide the level of protection that they want. And
right. Well, that whole category is called personal exposure monitoring.
Yep.
So as an individual goes from home to office or to a field site, then they can monitor their cumulative exposure over the day.
Okay, great. Thank you so much. This is very, very useful. Thank you very much, Yogesh.
Sure. I do want to come back to your question about where do you think the impact will be most. So as I mentioned, the biggest market is really in consumer applications, right now driven by cell phones. There I feel that one of the biggest opportunities is in healthcare and wellness monitoring. So having sensors that can provide medically relevant information, perhaps not quite as precise as you'd be able to get in a hospital with an expensive dedicated instrument, that can serve as a screening tool. And I also feel that there is a lot of potential in other biomedical devices, because this comes from miniaturization, right? This technology is associated with miniaturization. So one of the benefits is the volume, the smaller volume and the lower power it takes. Another benefit is the cost, right? So the automobile industry is using these sensors not because they need the size advantage. It's in most cases it's because the cost of ownership is lower as a consequence of having these sensors. The consumer industry, cell phones and so on, are using it maybe in some combination of size and cost. And they certainly wouldn't be using it if the cost wasn't low enough.
That's right.
Okay. But one of the places where the size is really the prime driver is implantable biomedical applications.
Implantable biomedical, correct? Okay.
Right. So if you had to put a pressure sensor in a blood vessel, you simply wouldn't go there. You simply wouldn't do it if it wasn't small enough. And the cost is only a secondary consideration because the cost of implanting the sensor is much higher than the cost of the sensor.
So Yogesh, do you think in the future trends of 3 to 5 years that we may actually go there in terms of where miniaturization will lead us to putting sensors in blood vessels to monitor the pressure and things like that?
Absolutely. It's not just pressure. It's also other parameters, right? So one of the things that our center has been pursuing for the past decade and a half are pressure sensors that could go and other types of sensors that could go inside a stent or inside a blood vessel. And what we've been pursuing for twice as long, going back to the 80s, is sensors that can go into the neural cortex. At the moment, they're still research tools, but you can imagine the diagnostic and therapeutic applications of brain probes. Right? And there's been some commercial activity there as well.
That's amazing. I can see business applications of that too, right? I mean, in terms of understanding consumers, how they think, and all the stuff is there. I mean, because there is a lot of work in cognitive marketing, they call, where you try to kind of instead of asking questions, you try to see what the brain changes, in terms of react to that.
Yeah, but I don't think we'll get to the point that somebody's going to accept an invasive probe for business. For business. It's a tool of last.
They may accept it for saving their life, but not for
exactly.
Fair enough. But this conversation has been fascinating. So thank you very much. It's been so helpful.
Okay.
It was very informative.
Okay. Understand pumps and certain energy
Today we have Sasan Chimori, who's the CEO of OmniSend, who's joining us for a conversation on some exciting technologies that they have implemented using sensors that we've been talking about in the class. Sasan, first, welcome to the course.
Thank you. Hello, everyone.
Sasan, you certainly, of course, are alum of the University of Michigan, and the story of OmniSend as a company started here in one of the research labs, correct? So tell us, first of all, of course, go blue, and welcome back virtually to Ann Arbor. Tell us about the journey of OmniSend, how it started, what is the company?
Sure. Back in 2016, I was designing the storage for supercomputers and building the fastest storage in the world for many Fortune 500, Fortune 100 companies. And I wanted to do something different that I could see impact the world, the health, the world, and so forth. And in one of the meetings that University of Michigan had, webinars or conferences University of Michigan had in Silicon Valley, I met Professor Yogesh Gechandani, the director of the MEMS lab at University of Michigan. And I asked him, what is the most mature technology that you're excited about and you think there's a chance for commercialization? And he mentioned that this micro GC, micro gas chromatograph chip that they have developed for the last 10 years is a very ripe technology and could be used. So that was the start of the company. And I was very excited to see that the smallest footprint, what they can do. And I took on myself to go and spend 6 months talking to different customers, regulatories, other customers, commercial customers, and to see what the response is. The response was very positive. I talked to CARB, which is the California Air Resource Board, which regulates the gas industries and pollutants and so forth. In California, they're a very prominent part of the government. I talked to one of the executives and I showed him what we have. And he said, where have you guys been? This technology is so advanced that we could use it like yesterday. So those were the very encouragements from the industry. And we decided to go raise some money and build the technology and commercialize it. And that's what the journey started. We raised some fund. We started hiring some talents, and we had a tie with the University of Michigan, which was very helpful, and we started the whole.
Great. So this is, of course, the MEMS Center headed by Professor Yogesh Gechandani is very well known, in the University of Michigan, and in fact, the university is very famous for that center and that work. So this technology, it's so exciting to hear the technology actually came out of the university's work. And you mentioned about GC sensors, primarily sensor technology. Can you explain what that GC? Can you explain for our learners what exactly does it mean?
Sure. Gas chromatography is a technology that has been around for the last 34 years, and that technology is used to detect different type of gases, and still is very, very used in industry today, starting from food industry to healthcare to oil and gas, you name it. When you want to analyze a compound in gaseous format or liquid format to see what kind of compounds exist in that particular sample, you use gas chromatography. And then what it is that basically you inject the sample, you let it, you collect the sample, you inject the heat or excite the sample so that in a gaseous format, the compounds start moving in the columns. So-called, these are the U-shaped structures that the sample moves based on the molecular weight of the sample. Some of the compounds fall behind, some of them come earlier. From the time that you inject the heat or you excite the sample to the time that you detect at the end of the columns, that's called retention time. Based on retention time, you can tell what kind of compounds you have. Now, the thing exciting about the University of Michigan development was that they shrunk this huge machine, that's the table-sized machine, into a little chip that's no more than 5 centimeters on the side. And that by itself is, and they also integrated pre-concentrator where you collect the sample, all in one chip. And that was quite exciting and very advanced. And I felt that this is the really leading edge of the technology, should be commercialized. And I was right. The type of customers we have is just certifies that.
So if I understand correctly, so this chip that is being developed at the University of Michigan, we can understand this is a very sophisticated sensor, which is complex and actually basically analyzes the gases through gas chromatography and then identifies the compounds within the gas, right? So fantastic. This is exciting. So just the sensor technology, there's an invention at the University of Michigan, right? Then you kind of you spawn this company, OmniSend. Now tell us about OmniSend as a company, as a business. What do you do? What services do you offer?
Right. So we wanted to make the product. The heart of this sensor technology is what would be licensed or we got from University of Michigan. But what we did, we built autonomous feature around this sensor where we have basically, if you look at our analyzer, it has no buttons, no switches, no levers, nothing. It just wakes up, connects to the portal through internet, and basically from your laptop or your phone, you could control and start the experiments or the measurements and then get the results right away. So we merged this sensor with the cloud technology in a broader picture. And there's a lot of advancements we made during the way where the information gets transferred to the portal, it gets backed up there. If for any reason internet gets disconnected, we store the data, continue collecting data, store it, and then transfer it. On top of it, we built some warning systems because where this device goes, the people using this device, they want to know if there are pollutants in here. There's an emission that they didn't know about it, unwanted emission. They want to know that. So we have a lot of warnings that the portals generate. They send text, they send email to command centers, and they warn them that we're detecting benzene, for example, which is very carcinogenic material regulated by EPA. And once they detect that, the command center needs to come out and take actions to contain that emission. So that's the company in a nutshell. We brought IoT technology. We took the sensor from University of Michigan, combined it, we applied it to different fields of the industry, and that's the product.
Great. So you have these products that are actually kind of sensing the gases in your customer premises. They're all connected back to your cloud platform, where they kind of have a common place where you can analyze, monitor the data, and also you can raise some warning signals and things like that based on the data. Wonderful. Yeah. So this is exciting. What kind of customers? For example, can you give us examples of your customers, say in the manufacturing industries or other industry?
Sure. One of the things that comes to my mind, which we're engaged right now, is the oil and gas refineries. EPA has passed a ruling back in 2015 that regulated the benzene at the refinery's boundary. Now, you're supposed to read 3 parts per billion or less. If you're reading benzene at the refinery's boundary at above 3 parts per billion, that means you're violating this rule. So a lot of these refineries started monitoring the benzene at their perimeters and reported to EPA. They're supposed to report to EPA doing the thing. So one of our customers has a refinery in Corpus Christi that has there's 2 refineries next to each other, and there's an emission of benzene. They don't know who is responsible for it, and there's a big fine if they get pointed to if there's an improvement that they're violating. They're going to have to pay fine. So what they do, they use our product as a production. They put it on their facility. The product works 24/7, and as the level of benzene rises, or we report that there's a violation, they look at the direction of the wind. We have a wind sensor that tells the speed of the wind and the direction, and based on that, they figure out where the emission is coming from. And in some cases, lately, that showed that benzene coming from the adjacent refinery, not from them. That was one instance. The other instance was that there's a truck came in that was leaking and parked there, and they were doing some work, and immediately the benzene level went up. They got warning. They went out there and detected, and they told the truck to move it out because it's causing trouble. So this is a production example. Or one of our big customers is Dow Chemical in Midland, Michigan. They use this one at their many areas that they have applications. Like one of them is on a shipping and receiving dock. There could be a lot of spillage of toluene, which is another VOC, and they use this device to detect that and take steps to remedy.
Yeah, I can understand. I mean, I can see that Dow Chemicals is one of the largest chemical manufacturers, and they will immediately find this very, very useful. In fact, even for general manufacturers, I think this can be a great safety device. Like, if there is any other any leak or any place, they can actually do this.
Anybody that has a VOC in their premises, like VOC stands for volatile organic compound, like benzene, toluene, xylene, styrene, methyl, and so forth. These compounds used abundantly in large quantities in different manufacturing around the world, and people want to take actions to make sure that they don't escape, they don't have emission, they don't have a leak. So our device can go there and autonomously report this situation.
And this is pretty exciting and relevant what we've been talking about in the class about the applications of sensor technology. So, Sassan, one last question before we end. So, where do you see the future of these technologies in terms of what are the potential applications, and where do you see the market? Which industries, especially next 2 to 3 years?
Yeah. So the immediate use right now is the oil and gas industry, wastewater management, industrial wastewater management, and that's a big field. Dow Chemical is obviously involved in that. Any manufacturing facility that deals with these VOCs, they could use this technology. The next one that we've seen coming up pretty hot is that healthcare, medical. There's a lot of work has been done in England and in Europe and some in the US that they monitor patients' breath. They call breath biopsy. And they look at the VOC content of the breath, and based on that, they decide this is the onset of tuberculosis, this is the onset of lung cancer, breast cancer, GI problems, and many other diseases. These are proven records and technology that have been published. And so, but we have not done any work on that area. But our device can be used in that front. Lately, we are part of a proposal to NIH for $4 million, where they're looking for a skin wearable VOC analyzer, where they could read the patient's or the person's VOCs are getting emitted from their skin, and based on that, they could decide this is a certain diseases that the person could have. And that's where the grant is. So the healthcare and medical is definitely heading that way of the VOCs, and they're using VOC detection as a means to decide what kind of a health condition is happening to the person.
Great. Thank you very much, Sassan. I mean, this is very, very useful. I really thank you for your time.
Thank you.
Transforming the rest biophysics biopsy from audition defect work being done in application of VOC quality organic compound sensor to monitor the rest of medical patient health onset of disease at tuberculosis, lung cancer, and breast cancer. This technology is called the risk biopsy. How might the red biopsy could be transformed from a traditional sensor application into an IoT application? So we will need a connection to the internet. That's it. To the lab. Concept violations. Okay. technology summarize. Okay, we will finish one and then next time we do.
Let's go back to the learning objectives that we started with and then revisit the content that we covered in the course. We started with understanding what is IIoT and then what is Internet of Things. That's how we started from Internet of Things and understanding how this connecting these things or devices to the network actually leads to enormous potential for application in the context of business and manufacturing. And then we talk about the building blocks of this technology, starting understanding the simple sensor technologies as examples of thermostat, and then starting with the simple thermostat, how you bring the cloud computing capabilities. We refer to the new cloud architecture and the edge architecture, what the combined intelligence that they bring together, and when you kind of connect these devices into those capabilities, then it gives a special opportunity for companies to access the data and the insights ubiquitously from wherever they are, and that leads to a lot of information, a lot of contextual insights that can be converted into business value. We talked about various dimensions of business value benefit that can come in the manufacturing context from these IIoT applications, and then we went through about 5 dimensions of that, and there's a lot more, including making the manufacturer more green and environmentally sustainable. We went through a 6-step implementation framework for managers to understand that what kind of challenges they may face and what are the do's and don'ts and what steps they need to take to make sure that they have identified the problems right and they've made the choice of the problems right, and they kind of have the right executive sponsors, right partner ecosystem, both internal and external, understanding the compatibility issues to make sure that it works with the kind of infrastructure they have, and finally execution and putting the change management process in place with all the leadership support. And we then moved on to discuss these challenges, critical challenges, and the risks that come to this technology, and we kind of amplified some of the risks like cybersecurity and the risk coming from cost, two sides of it, and also risk from the talent, also both challenges and risk, because this requires nurturing new talent, nurturing new approach to building talent, and understanding the new capabilities. We covered some of those aspects in depth, and finally, last we spent some time understanding the future trends in this technology and what we can expect going forward in the next 3 to 5 years as they kind of emerge and redefine the future of manufacturing.
Okay. So yes, video here. So